Don't forget to subscribe and ring that bell.
Here we are, my friend. We are at the end of yet another calculus journey as we finish the final free response question of a set of practice problems from 2022 for the AP Calculus ABA course. And we don't get a calculator, which, you know what? It's all good. I ain't mad because I'm smart and I know you are too. You're here. That means you want to learn or you want to check your stuff. Okay? That denotes intelligence. So without further ado, let's start the end. Free response question number 6. Number 6 reads, particle P moves along the x-axis such that for time t greater than 0, its position is given by xp of t, which is 6 minus 4e raised to the negative t. We have particle Q, which moves along the y-axis such that for time t is greater than 0, its velocity is given by vq of t, which is 1 over t squared. At time t equals 1, the position of particle Q is yq of 1 equals 2. 6a is asking us, find the velocity, okay, vp of t, the velocity of particle p at time t. Now, there's a lot of letters here, p's and q's and v's and a's and just whatnot, not to forget t's. So let's make sure we're looking at the right thing. If we want the velocity of particle P, okay, here's P. I'm going to go up here. We know the position is this right here, okay? And we should know, this is calculus, and it is not our first day, that velocity of P is the derivative of the position of P at time t, all right? So I'm going to have to take the derivative of this thing in the upper right corner here. The derivative of 6, well, that's just going to be a 0. It's going to go away. So I'm really taking the derivative of this term right here. That negative 4 out front, all right, it's a constant. I'm just going to leave it. Okay, so it's negative 4. So I'm just going to write like negative 4. Anytime I take the derivative of E, I always start by rewriting it. E to the negative t. I rewrite it without changing it. And then I do a chain rule, meaning I multiply by the derivative of the exponent. The derivative of negative t is negative 1. Now I just simplify. All right? A negative times a negative is positive. So I have positive 4 e to the negative t. Perfect, 100% credit. If you want to bring that e down, you can. You can say 4 over e to the positive t, but, I mean, that's overkill. Don't reinvent the wheel. Get your answer. It's accurate. It's correct. So you move on. 6b, it asks us to find acceleration, aq of t, the acceleration of particle q at time t. All right? Then it says find all times t for time t greater than 0, when the speed of the particle is decreasing, and justify your answer. All right, so we have 2 tasks here. First, we need to find acceleration of q. Again, we have so much here. Let's find q, which is here, and the velocity is this thing right here. Beautiful fraction, all right? So let's first find the acceleration. We'll worry about the speed decreasing afterward. So in order to find acceleration of q, you need to take the derivative of the velocity of q. So I'm going to take the derivative of this fraction right here. Now, the first thing I'm going to do is I'm going to take this denominator and bring it up. And I can negate the exponent. So that's really t to the negative 2. It's a lot easier to take the derivative of something that has an exponent without a fraction than it is to do the quotient rule, which is what I would have to do. Now, if you still do the quotient rule, that's fine. You would still get a correct answer. But I'm going to do the easier way. All right? The derivative of t to the negative 2. The negative 2 comes down, and then I subtract 1 from the exponent. There you go. That's it. Now, if I wanted to, okay, this is the equation for acceleration of particle q. But if I wanted to, I could take the t and the negative 3, and I could flip them within the fraction and make that positive. So if you do the quotient rule, maybe you came up with this. They are the same exact thing, and either one would get you full credit. Okay, so that's the first part of 6b. The second part, okay, is find all times for t where t is greater than 0 when the speed of particle q is decreasing. Okay, let's do a quick little review on speed, shall we? I need to take a look at the velocity and the acceleration to determine if the speed is increasing or decreasing. And this is like a scalar representation, meaning, for a lack of better terms, and to try and simplify that as much as I can, it's like multiplication. If the signs are the same for both of these, whether they're both positive or both negative, the speed will be increasing. If the signs are different, and it doesn't matter which one's the negative and which one's the positive, my speed would be decreasing. Now, this problem is asking me to find when the speed is decreasing. So I don't care when they're positive. Okay, so I don't care about these right here. We're just going to try and find a situation for particle q where my acceleration and velocity are different signs. Okay, so let's go ahead and start that process. All right, the velocity of particle q was 1 over t squared. And we just came up with the acceleration for particle q. That is -2. I'll use the fraction. This one right here. When we're evaluating, like we have to here, it's always easier to have a positive exponent. So that's why I'm using the fraction. Okay? So first of all, do we have any limitations? Okay, do we have any limitations on my variable for t? And I do. If I look up right here, t is always positive. That's a plus sign, not a t. So t, now it's a t, that's why I make the little tail at the bottom of my t's, is positive, always. Okay, it can't be 0, because what happens if I look at velocity and acceleration, I can't have 0 in the denominator, it would be undefined. So time has to be a positive value. So let's take a look at velocity here. If time is positive, and I square a positive number, I will have a positive denominator. And this will always be 1. It will always be a positive 1. Positive divided by a positive will always give me a positive velocity. So as I look to my chart to the left here, velocity is always positive. So it's not this situation here. Let's get rid of that. Okay, so I need to take a look at my acceleration, and I want to see when my acceleration is negative. Because if I look at my chart here, I'm right here. My velocity is positive. I want to find out when my acceleration is negative. That's how I get a decreasing speed. All right, so let's take a look at our acceleration here on the right side of the board, keeping in mind this up here that my time is always positive. So again, if I take a positive value for t and I cube it, it will always be positive. Okay, this top never changes. There's no variable up there. It will always be a -2. Anytime I put a negative over a positive in a fraction, I will always end up with a negative value. So my acceleration, good for us, is always negative as you look over here on my little chart. So if my situation, okay, is that I always have a positive velocity and always have a negative acceleration, my speed will always be decreasing. So when's the speed decreasing? Always. So I don't know. I mean, justification in this case, because I didn't do really calculations, I'll just write up a little snippet here. And I will say, speed is always decreasing. And I'm going to use decreasing because that's what they did. Since velocity of q is always positive and acceleration of q is always, you guessed it, negative. Okay, this is justification to me. That is absolutely wonderful explanation and justification. We have our acceleration equation on the top, -2 over 2 cubed. And then we have our justification and, I guess, answer to whether the speed is increasing or decreasing, or when it is decreasing, always. Right, 6b, done. All right, 6c. Find yq of t, the position of particle q at time t. Here we go. Now we're going to start. Now we're not just doing a derivative and an explanation here. Now we're finally doing some calculus here. I mean, A and B were calculus, but you know what I mean. We're going to start doing a little bit more rigorous math. Let's identify what we need, what we're doing here. Okay, we need position of particle q. So for particle q, we have velocity. That's this thing right here. Oh boy. All right. And find the position means we just want the equation at time t. So in order, all right, and man, you better have not forgotten this. Let's go here. What other things? Purple. I'm in a purple mood here. Okay. If I have velocity and I want, I'll move that over, and I want position. Okay, if this way is the derivative, okay, I'm going backward. I need to integrate. You better know that. That is a basic thing. So I'm going to integrate my velocity. And again, I'm going to change that so it's t to the -2. Okay, I'm going to bring this up and negate the exponent. It's always easier to work when I have a term that's not a fraction and has an exponent. Okay, now don't forget, dummy variable. They will take points off if you don't have the dummy variable written. Why? It's just a dummy variable. Stop it. Stop it with your ignorance. You need the dummy variable. Now, there are no bounds. So when I integrate this, I'm going to have to put plus c. All right? So remember, it's the opposite of derivative in the opposite order. The first thing I'm going to do is I'm going to add 1 to this exponent. Okay, so that's going to be t to the -1 and divide it by that new exponent. So I really have -t to the -1. Or if I want, I could just call that -1 over t. All right, because technically this is over 1, and I could bring this down and whatnot. All right, so that's a t right there. And now, since I didn't have bounds, like I said, plus c. This is position. Oh, they say y of qt. But when they want the equation, I can't have the c here. I got to get the number for that. All right? And this is called an initial condition problem, which means they gave me an initial condition right here that's going to help. When t is 1, my position, I guess I should call that y of q, is 2. All right? So when t is 1, my position is 2. All right? So let's go ahead and figure this out. Okay? -1 over my t, which is 1, plus c equals 2. Well, I mean, you know, I said we're going to do some rigorous math. It doesn't look like it, does it? -1 plus c is 2. If I add 1 to both sides, boom, c is 3. So I'm not done. Don't celebrate yet, okay? I've got to take that 3 and I've got to put that into my c, because this is the equation, right? It is. So let's finish this off. Y q of t, position of t, is negative. Oh, that's just horrible. What I put that equal sign right in the parenthesis. Tisk, tisk, tisk. Equals -1 over t, and c is a positive 3. That, my friends, is the position of particle q. Look at us go. It's like we know what we're doing. All right, this is it, guys. Oh, man. Kind of getting a little emotional here, but you know what? Let's not let it fog our memory and our knowledge and our processing skills. Let's just bang out this problem. D says, as t approaches infinity, which particle will eventually be further from the origin? And give a reason for your answer. All right, well, let's do some math, shall we? Now, when I see this, I immediately think limits as a variable approaches a value, all right? So what we got to do is, what is farther from the origin, right? So just for, stepping back and looking at our situation here, explaining the situation, we have particle P that's on the x-axis, all right? We'll call this particle P, somewhere on the x-axis. And then we have particle Q, which is somewhere on the y-axis, all right? As time goes by, P is going to go further. The position of P is going to move. Which one's further, okay? Further away from the origin, okay? So Q is going to start going boom, P is going to start going boom, and which one's furthest? So I want to know the position, okay? Because whatever the position is, let's say this P is at position 6. Well, if we're at the origin, that's 6 units away. And let's say Q is at position, I don't know, 4. Well, from the origin, that's 4 away. So whatever has a bigger number for position as t goes to infinity, that's going to be further away from the origin. So I'm going to need the position for particle P and the position for particle Q. They give us the position for particle P right here. So x of P with respect to time is 6 minus 4e to the negative 1. All right? And for 6c, we just figured out what the position for Q was. Okay? So there was a reason we had to do that. So on the y-axis for Q time t, that was 1, well, negative 1 over t plus 3. So let's take the limit as t equals to infinity of both of these and see which is a bigger value, because that will be farther from our origin, all right? Let's start with particle P. So the limit as t goes to infinity of 6 minus 4, I'm going to change this into a fraction. I'm going to take this and pop it down here. Earlier, I don't know if it was for 6b or 6c. It doesn't matter how you write your answers, but when you start, is that a negative e to the negative t? It's a 1 there. That's weird. I don't know if I drew that or erased it. But when you start to evaluate these things, it's always better to have the positive exponents. All right? There you go. So all I'm going to do, I can't reduce, I can't say, hey, the biggest term in the top, the biggest term in the bottom, because there's only one term in the top for the numerator and one term in the bottom, the denominator, for that second term. The 6 will just stay there. Now, as I'm going to plug in my infinity now, because there's nothing I can really do. So I've got 6 minus 4 over e to the infinity. Okay? Oh, you best know this. The bottom of this fraction will get bigger and bigger and bigger, and the top will stay the same. If my fraction, if the denominator, the bottom part, gets bigger and bigger and bigger, infinitely bigger, and the top stays the same, that fraction will approach 0. Okay, 6 minus 0. So it will approach the number 6. The further and further it goes, time-wise, the closer and closer it will get to 6 units away from the origin on the x-axis. All right, well, let's do the same thing with y and see what's up. Let's compare, see what's up. So again, I'm going to take the limit as my time goes to infinity. I'll do it a different way this time. Of negative 1 over time, or t, plus 3. All right, again, we can't simplify. There's one term in the top, our numerator, and one term in the bottom, our denominator, for our first term in this polynomial, okay, this binomial, I should say. And the 3 is just, I'm going to just leave it. There's no variable there, okay? So I'm going to say negative 1 over infinity plus 3. Man, for a 6D problem with limits, this is easy. I mean, I don't know if the trick is to realize you got to use limits. But man, again, if the bottom gets bigger and bigger and the top stays the same, okay, this just keeps getting bigger and bigger and bigger and bigger, it will eventually go to 0. This, there's no t in there, so there's nothing. That will stay at 3. 0 plus 3 is our 3. So the limit as t goes to infinity of yq of t, of my position of particle q, that's 3. So which one's further? P is. Why is P further? Because 6 is bigger than 3. So on the x-axis, we're 6 units away from the origin for particle P. And for particle Q, I'm only 3 units away from the origin. So this work is all nice, but it says, we got to answer this. Which one will be farther? And give you a reason. The reason is quite simple. Let's not overcomplicate things, okay? Particle P will be further. And look up here. You see how it says eventually be further? I'm going to say will be further. I'm going to put comma eventually. I like to use their words. Eventually, comma, since 6 is greater than 3. I mean, very basic explanation. Oh, I don't know if you heard that. Our school got new bells. Those are really, sounds like someone's whacking a cowbell. Sounds like someone's whacking a cow. We need more cowbell. Okay, sorry, I can't do my Christopher Walken yet. I haven't warmed up. But anyways, if I were to ask you to explain why particle P is further than particle Q, and you were in my class, you'd look left and look right, and you would say, because 6 is bigger than 3. And you'd be correct. So write it down in your paper. We're done. I wish you the best on your AP Calculus exam. I know you are going to knock it out the park. And hey, you want to leave a comment, do whatever. I love hearing from people. I will see you later. Bye-bye.
Don't forget to subscribe and ring that bell.